Now let's work on some very nice variation of parameters problems. So when we have a non-homogeneous second order ordinary differential equation, one of the methods we could use was method of undetermined coefficients. And method of determining coefficients is pretty useful. However, in some cases, just like the one we have in front of us, we would not be able to use method of undetermined coefficients because we would not be able to guess our particular solution because we don't have a guess for tangent. However, we can use variation of parameters, and it would work out really nicely for pretty much every function we have on the right hand side. So we could go ahead and use variation of parameters to solve this problem. So I'm going to start with getting the homogeneous solution. So we will have r squared plus 1 as a characteristic equation. R squared equals to negative 1, and our roots will be r1 comma 2 is plus or minus I. And this means our homogeneous solution YH is going to be C1 cosine of x plus C2 sine of x. Guys, if you don't remember this, just go ahead to the first few lectures and we cover this for complex solutions of homogeneous differential equations. Now that we have our homogeneous solution, I would like to get the fundamental set of solutions, and that's going to be a cosine x, comma sine x. And let's just go ahead and find our Wronskian. So we will have a negative sine x here and a cosine x here. And if we cross multiply, we're going to get cosine squared x minus sine squared x. So Wronskian ends up being 1. So since we got our Wronskian, let's find y particular, which is u1, y1 plus u2, y2. Well, we need u1 to solve that. So u1 is going to be the negative integral of y2, and y2 is sine x multiplied with the non-homogeneous part, tangent x, divided by the Wronskian. However, our Wronskian is 1, so I'm not going to divide with 1. So we would have this expression right here for u1. So u1, in other terms, is going to be this is actually sine squared x over cosine, okay? And we could write that as negative sine squared cosine if we carry out that negative, so we would have this integral. And we could just write that as cosine x minus secant x dx. Okay, guys? If we use this trig substitution, it will be really useful to us because we are able to separate this integral into two pieces. So it will help us really nicely to solve this different u1. So if we check this, we have a 1 over cosine here and a cosine. Cosine squared minus 1 is sine squared. So we do have the correct identity here. So I'm going to go ahead and separate this integral. So we're going to have a cosine x dx minus integral of secant x dx. So over here we're going to have sine x, and over here we're going to have negative ln of secant x plus tangent x. Okay, and this is our u1. I'm just gonna leave that right now, and we're gonna multiply that soon with cosine x, which is our y1, to find the first part of the particular solution. So now let's go ahead and solve u2. u2 is going to be the integral, positive integral of cosine x times tangent x, and this cosine x times tangent x is just sine x. Okay, so we're gonna have a sine x dx here, and the integral of sine x is just negative cosine x equals to u2. So let's go ahead and build our particular solution. Our particular solution will be we're gonna multiply this whole expression sine x minus ln x ln secant x plus tangent x with cosine x. So we're gonna have cosine x sine x minus cosine x ln of secant x plus tangent x. Okay, actually, you know what, I'm just going to write that in a cosine factor, so we would have a more clear expression. So I advise you guys to do the same. Sometimes using these factors are really helpful also for your professors to read cleanly your work. Okay? So we would have this first piece over here. I'm going to carry this a little to the downwards. Okay? A little over here. And okay, now that we have this, we're gonna get u2 times y2, and y2 is sine x and u2 is negative cosine x, so we're gonna have negative sine x cosine x, and as you can notice, we have a cosine x sine x over there, so we'd actually cancel those out. So in finally, we would have negative ln of secant x plus tangent x as our particular solution, and therefore our general solution will be c1 cosine x plus c2 sine x, our particular solution, minus, okay, minus ln of secant x plus tangent x, just like this. One final note, guys. Really important. We're distributing this cosine x to inside, so we would also have a cosine x factor over here. It's a small algebra mistake, but you guys please keep an eye on these small factors, especially when you're multiplying with parentheses. Sometimes they do get lost. So finally, our solution will be just like this on the screen. Now let's solve this undetermined coefficient problem. Now let's solve this second order ordinary differential equation problem. Over here we have a y double prime minus y equals to e to the 2x. So guys, we can solve this problem using method of undetermined coefficients as well, and it would work out perfectly fine. But I want you to solve this using both methods. But use method of undetermined coefficients and then try using variation parameters and try to see if you can get the same results and then compare your work. Because if you can master these problems solving both methods, that means that you have mastered this concept, and it's really essential for you to know because they ask you both of these concepts in many exams about differential equations. So it's really important for you to know both methods. So we will have r squared minus 1 as our characteristic equation, r squared equals to 1, and our roots will be r1 comma 2 plus or minus 1. So we have distinct real roots. Our our YH homogeneous solution will be C1 e to the t plus C2 e to the minus t. Actually, we have a x variable here. It is important to watch out for variables, so we would have c1 e to the x plus c2 e to the minus x. And our fundamental set of solutions, y fundamental, will be e to the x, comma, e to the minus x. And now I want to find the wrong skin because we're going to use it. So we're going to have this, and negative e to the minus x. So if you cross multiply, we would get negative 1 minus minus 1, and that will be just minus 1, so we would have negative 2 as our wrong skin in this example. So we would just cross multiply, get negative 1 minus negative 1, and minus 1, so we would have negative 2 as our wrong skin. So let's find our y particular. Okay, and our u1 is going to be the negative integral of y2. y2 is e to the minus x times the non-homogeneous part, e to the 2x divided by the wrong skin, dx. So u1 ends up being 1 over 2 integral e to the x dx. Well, e to the x dx is e to the x, so we don't have to worry about that. So this will be our u1. And if we want to find u2 will be the integral of y1 e to the x multiplied with the non-homogeneous part divided by the wrong skin, and u2 will end up being negative 1 over 2 integral of e to the 3x. However, integral of e to the 3x is just 1 over 3 e to the 3x, and therefore our u2 will be negative 1 over 6 e to the 3x right here. So we would have both u1 and u2, and we have our fundamental set of solutions. Well, we can go ahead and build our y particular. Y particular will be u1 y1. u1 y1 is 1 over 2. E to the x times e to the x is e to the 2x. Okay, and u2 y2 is going to be, we're going to just subtract e to the x from the exponent, so we will have negative 1 over 6 e to the 2x. And nicely, we have two e to the x terms here, to the same exponent terms, so we would be able to factor this as e to the 2x multiplied with 1 over 2 minus 1 over 6. And that will be 2 over, I'm sorry, if we multiply with this 3 over 6 minus 1 over 6 becomes 2 over 6. Well, then that's going to be 1 over 3. So we would have, I believe, 1 over 3. Yeah, y particular is going to be 1 over 3 e to the 2x. Okay, just like this. And now that we have our y particular, we can go ahead and build our solution. So y general will be c1 e to the x plus c2 e to the minus x plus 1 over, I'm sorry, yeah, 1 over 3 e to the 2x, like this before. Last but not least, we have this differential equation problem, y double prime minus 3y prime plus 2y equals to e to the x. So as I said before, we can use method of undetermined coefficients, and I advise you, please try solve this, both methods, to master your knowledge in this concept. So I'm going to try solving this using method of variation of parameters. So we would have this characteristic equation, and our roots, our factor will be just like this, r minus 2 and r minus 1. r1 will be 2, r2 will be 1. So our solution will be c1e to the 2t, to x, I'm sorry, because we're dealing with x, keep an eye on that. Sometimes they do get mixed up. I know we use a lot of x's and t's in differential equations. It is crazy. So we have this differential equation solution, homogeneous solution, and we want to get our y fundamental. Y fundamental ends up being e to the 2x comma e to the x. Okay, so if we made a guess, guys, we would have an a e to the x term. However, this contradicts our y fundamental, because we do have an e to the x term in the y fundamental. So we would multiply this with x to remove this dependency, which is a problem in undetermined coefficients, but you don't have to worry about that in variation of parameters, because we do account for that and we don't really rely on guessing our solutions. So I want to find our Wronskian. So our Wronskian will be, we're going to have this. So we're going to multiply e to the 3x minus 2e to the 3x, so our Wronskian ends up being minus e to the 3x, just like this, okay, equals to Wronskian. Now that we have that, we can go ahead and find our u1 and u2, and then get y1 u1 plus y2 u2 equals to y particular, and y particular plus y homogeneous is y general. So u1 is going to be the negative integral of the second solution, e to the x multiplied with the non-homogeneous part. So we will have e to the x multiplied with e to the x, so it's just e to the 2x divided by negative e to the 3x dx. And this means u1 is going to be equal to integral of 1 over e to the x, or e to the minus x in other words. So I want to write that as e to the minus x, okay? E to the minus x, and that just ends up being negative e to the minus x equals to u1. Very simple, very nice. And let's go ahead and find u2. So u2, just like YouTube, is going to be integral of y1 e to the 2x multiplied with e to the x, which is our non-homogeneous part, divided by the Wronskian, negative e to the 3x. So our u2 is actually the integral of negative 1 dx, and u2 ends up being negative x, just like this. And now we can just go ahead and plug these in to get y particular. So y particular will be y1. y1 is what? E to the 2x. and what you want is minus e to the x, so minus e to the x. Okay, this negative x will take 1 from this e to the 2x because we're multiplying them, and plus u2 y2, so e to the x times minus x, so we would have negative x e to the x. And this is going to be, guys, our particular solution. And now we want to combine this with our solution. However, guys, notice that we have a negative e to the x here and a c2 e to the x here. So we don't have to write this because this will get absorbed into this. We will have e to the x parentheses c2 minus 1, just like this. And that's actually another constant, so we don't have to actually write this term. So our only the reason why we have this is because we have a dependency with e to the x. So that's why we were going to multiply this with x for undetermined coefficients method. So if you multiply it with x, you will get only this solution for y particular, and you're not even going to get this solution. So that's why you're avoiding this dependency. However, in this case, since we're not doing that, we're going to avoid this dependency by just not writing that, because it's just meaningless to have this negative e to the x term with c2 e to the x in the left hand side, because it just doesn't make sense. So you don't want to have this term. Okay, guys, this is really important. I mean, it wouldn't be mathematically incorrect, but I don't think many professors would like you having that, because it would quite show you that you don't really grasp the concept of these constants. So our y general will be c1 e to the 2x plus c2 e to the x minus x e to the x. And this is our general solution for the differential equation.